Hello everyone, this is our first KVL example. We're going to go ahead and apply KVL for a very simple circuit so we can see how we consistently apply it and find an unknown voltage. Here's the circuit we're going to be looking at. In this circuit we have an independent current source of 2 amps and then we have 3 resistances and all of these components are in a single loop. The question is to find the voltage drop Vx that is across the circuit, the 2 amp current source with the polarity shown in the figure. Once again, as a reminder, for an ideal current source, you cannot directly find the voltage drop across it. That's because that voltage drop can be anything. It really depends on what circuit you have connected to your ideal source. So there has to be another way, another strategy that we can apply here. This other strategy is clearly to link Vx to all the other voltage drops on that simple loop so we can apply KVL and find it. Now, applying KVL, as we have learned before, first of all requires that we have at least written down the voltage drops that we want. So here notice, for example, that I have assumed V1 with a known polarity, I have assumed V2 with a polarity shown there, and I have assumed V3. Once again, these assumed polarities may or may not be correct, and that's okay. The important thing is to assume a polarity and stick with it for the whole problem. So with these polarities, let's go ahead and apply KVL. So KVL will give me the following. I'm starting from my lowest left corner, which is this one right here. I'm using clockwise direction, as you have learned in the KVL video. And I'm using the first sign I encounter as the polarity for the voltage. So the first voltage drop that I see is Vx with a negative sign. So this would be negative Vx. The next voltage drop I see is V1 with a plus sign. So this would be plus V1. The next voltage drop I see is V2, also with a plus sign. So there will be plus V2. And finally I have V3 with a plus sign as well. So the equation is negative Vx plus V1 plus V2 plus V3 is equal to 0. Or Vx, the unknown voltage, is nothing else but V1 plus V2 plus V3. Now, each one of those voltages, V1, V2, and V3, are actually known. Well, they're not directly known, but they can be found very quickly by applying Ohm's law. Why? Because I know how much current flows. This is a simple loop, so this current that you will have from this current source, the 2 amp, must continue flowing through all of these components. As we have learned before, these are connected in series, so they will have exactly the same amount of current. So for example, V1 must be equal to 2 amps times 5 ohms or 10 volts. Similarly, V2 must be equal to 2 amps times 10 or 20 volts, and finally V3 must be equal to 2 amps times 20 or 40 volts. So when I add all of them up together, I will find my Vx that is equal to 70 volts, and that is the right answer for the problem. Now you might ask the question, wait a second, what would have happened if I had chosen a different polarity? For example, I have exactly the same problem, but instead of V2 this way, I actually choose V2 this way, with this red color. If you had chosen V2 that way, then the only difference would have been that when you would have applied KVL, you would have written negative Vx as I did, plus V1 plus as I did, but then you would have negative V2, because the first sign you will see would have been negative, and then plus V3 equal to 0. But you may wonder, wait a second, wouldn't that have changed the value of V2? The answer is not at all, because by the time you get to apply Ohm's law, which is right here, to find the voltage V2, you would have seen that now with your red polarity, you have to write V2 as negative 2 times 10. And the reason for that is because now your current is entering the negative plus of your voltage drop, which means that as far as the 10 ohm resistance is concerned, you're now in the active sign convention. And in the active sign convention, we have that V is equal to negative IR. So now you can understand and see a little bit in more detail why it was so important to learn Ohm's law correctly. Ohm's law did say that V is equal to IR, provided that you have passive sign convention. Now, with the new polarity of V2, I have an active sign convention, and therefore V is equal to negative IR for that resistance. Notice for the 5 ohm and the 20 ohm resistances, I have passive sign convention. I have plus minus here with my current entering the resistance through the plus sign, and I have plus minus across the 20 ohm resistance with my current entering also from the plus sign. So the 5 and 20 ohm resistances have passive sign convention. That's why V1 stays the same, 10 volts, and V3 stays the same, 40 volts. But with the red polarity, the new chosen polarity, V2 must be equal to negative 2 times 10. And so, of course, at the end, the result will be identical, and Vx, it will still be equal to 70 volts as we found before. So in this example, you have seen a good way to apply KVL for a simple loop, and you have seen how careful you have to be with the passive or the active sign convention when you apply Ohm's law to find voltage drops across resistances. So thank you very much for watching this video. Talk to you next time.